like to welcome you. Thank you for coming to the SETI Institute Lunchtime Colloquium Series. We have these every Wednesday at noon on a wide variety of topics. You can, before we get in with today's talk, let me just tell you a little bit about the series. You can find out all about upcoming talks on our website. Just go to www.seti.org, click on the picture of Frank Drake that says Science Lectures, and that'll take you to the Colloquium webpage. From there, you can subscribe to our email list to find out lists of upcoming talks. You can also check out the archive of past talks. We videotape all of these talks, and so if you miss a talk, you can always go to that webpage about a week or two later, and you'll see that we've put up a video you can download and watch at your convenience. And because we do video these talks, we ask that you hold your questions, if at all possible, until the end of the talk, and then wait until I come by and bring you this microphone. If you notice, this isn't amplifying my voice. What this is doing is just capturing my audio so that it goes on the video, so that your question can then go into the archive of the talk as well. If you just ask questions from the back, then we don't always capture it, and so that the video archives just have gaps in them that can be kind of odd if you're watching it later. So I'd like to tell you about next week's talk. It'll be by Ross Beyer, and it'll be about the new inclusion of Google Mars. So he'll tell you all about how Mars data was integrated into Google Earth, and show you some really cool and amazing demos, I'm sure, of how you can use this great new tool for fun and also for science. So this week, it's my pleasure to introduce Scott Sandford, who's a member of the Astrochemistry Lab over at NASA Ames, and who is also a member of the Stardust mission. And so he'll be giving us some results for that mission.
Okay. Yeah, thanks for having me. Everybody will want to have a pair of these as we get into it. These will only actually help you in any way, shape, or form on a few select slides, but if you want to wear them for the whole talk as a fashion statement, that's fine. But they won't do you any good except for certain select slides where I'll warn you. Okay, I was asked to come and talk about the Stardust mission, and my title actually specifies that I'm going to talk about organics. I'm actually going to take a somewhat broader view in my presentation and give you some background on the Stardust mission, and also talk about some things that are not specific to organics but that play into the whole issue of an interpretation of the data we got from Stardust. So I'm going to take a fairly broad view of the subject area I can talk about, but I will, the end of my talk will be specifically about organics returned from this comet called Wild-2. I know it looks like it's spelled wild, but it's pronounced Wild. It was discovered by a Swiss gentleman who had an automated telescope looking for supernova and external galaxies, and he thought he had found one when he found a big fuzzy patch with a little speck of bright light in the middle of it, and so he came back the next day. The whole galaxy had moved somewhat to the left, so he's found, I think, 7 comets in all. This is the second one. He actually came to the launch of the spacecraft. We invited him, and he came to launch, so I got to meet him. And I think to this day, despite the fact that, of course, this comet is now somewhat famous, he was still sort of hacked off it wasn't a galaxy with a supernova. But anyways, he's certainly a man who has his convictions about what was interesting. Okay, so let's see if I can get this to advance here. Okay, the Stardust mission was a mission to go to a comet and collect a sample. Here's pictures of the thing in assembly and getting ready for launch. It's a fairly modest-sized spacecraft. The main bus is about the size of a desk. This is the only part that came back to the Earth. This is the return capsule that had the sample in it. Most of the other pictures I'll show of you will all be artist conceptions, of course, because we don't have any pictures of it in flight. And any other pictures associated with it will be pictures that it itself took. Now, given the new administration we have, and in the interest of full disclosure, I should point out that Stardust is also a candy bar, or was a candy bar, I should say. Did anybody see this when it was out? I completely missed it when this came through. Apparently, Nestle's, for a brief period in the late 90s or early noughts, made 9 different candy bars that had different NASA missions on them, and for some reason they picked Stardust as one of these. And I missed it at the time, but I got several of these candy bars because one of the co-investigators on the mission, Mike Zelensky from Johnson Space Center, found out about them. And he went down to the store, and they don't have on the label which one it is. So it's like collecting, baseball Pokemon cards or something, So he bought a box, he took them home, he opened them up until he found a Stardust one, and then he rewrapped that Stardust one, and he practiced feeling it through the wrapper. Until he could recognize a Stardust candy bar. And then he went back to the store every day after work, and he felt up all their candy bars, until he'd accumulated enough of these to give to all his co-investigators. I don't know what's more disturbing, that he had the time to do that, or that he could do that in a grocery store and no one would ask him what he was doing after a month or so. Any event, I got several of these when by way of celebration when this sample came back. By that time, the candy bar was almost 7 years old, and it tastes even better than you might have imagined. Okay, now before I really get into the details of the mission, I want to talk about a few general things. So I apologize, but I'm going to proselytize for a moment. Most missions that NASA flies are missions that do in situ science. They go someplace and they measure things, and they run around, they take pictures, they bang on things, whatever. NASA's done very few sample return missions where you go to a place, get a sample, and bring it back to Earth for study. And this actually, obviously, one of the reasons you don't do that is it's somewhat more complicated. You have to not just get there, you have to get back, okay? And that makes a much harder design problem for the spacecraft. But you have some amazing advantages if you can do that. And these are just a few of them. First of all, as I think most of you will appreciate, if you send a mission to Jupiter, it arrives there with analytical devices, with instruments to measure things that are really not state-of-the-art. First of all, they've been maybe spending 10 years cruising there, so they're at least that much out of date. But in addition, you don't fly state-of-the-art equipment on spacecraft. You want to fly a robust stuff that's space-proven. And so usually the stuff you load on initially is already out of date in many respects. Whereas if you bring the sample back here, you're actually measuring it in laboratories on the Earth, and so you can take it anywhere you want. And so you can put it in state-of-the-art instrumentation to make your measurements. And so you really get really the best you possibly can get in precision, sensitivity, resolution, reliability, all these things. And none of that requires you spend money on the spacecraft. In addition, the return samples are a resource for current and future studies. Okay, when we get a sample back from Stardust, we didn't study for 6 months and say, oh, well, that was cool, and throw it in the garbage can. It all goes to the curator's office at Johnson Space Center, where we keep the Antarctic meteorites, the Apollo moon samples, all these different materials, and they're available for study in perpetuity. I mean, there are still people studying and writing papers about scientific results on moon samples that were brought back in the 60s and 70s. And so any sample you bring back ends up being available for future studies. And this actually can have another advantage, which is you can measure these samples using analytical devices that you didn't even know about or have thought of at the time of the launch. If 20 years from now someone invents psychic infrared spectroscopy, we can take the Stardust samples out and measure them. We don't have to go back to a comet, and carry said device there to get a measurement. Also, the analyses are iterative and fully adaptive, and so you get a huge advantage of the fact that you're not limited by your current ideas in particular. If you want to send a probe to Jupiter and you're interested in something about the magnetosphere, someone will say, well, I think the main thing we need to measure is A. We need to know what the value of A is, or we don't understand the model. And you go there and you measure A, and the main thing A tells you is that you probably should have measured B. Okay? Now you have to build a B device and get it there. But and if you have the sample back here, you measure A, and if what it tells you is you should measure B, fine. Go down the hall, a B measuring machine. Just get on with this. Also, you avoid limitations associated with cost, power, mass, and reliability. So I'll show you some data later in this talk. It was taken using an accelerator, a synchrotron accelerator, which is not only bigger than the Stardust spacecraft, it's bigger than the launch pad the spacecraft left from. This is a kind of measurement you will never make in situ until we develop the Star Trek warp drive or something. There's just simply no way to get that kind of mass to these locations. And then, of course, the other thing is when you bring the sample back, you can give it to lots of different people who can all measure it independently, so you can make sure that your measurements are replicated, they can be verified, you can compare results against each other from different techniques. I mean, this is basically a fancy way of saying you give it to scientists and they'll all get together and argue about it, and the net result of that will be a better understanding about what's going on. Okay, and in particular, for Stardust, we went to a comet, and there's a reason why getting a sample from a comet is a desirable thing. Comets sample a unique part of the solar system's history and also a unique location within the solar nebula from which everything formed. We know our solar system formed from material in a dense cloud collapsing into a disk, and ultimately out the back end came planets. But a little bit of that material was left behind in smaller bodies, including the comets, which we think formed in the outer part of the solar nebula. And so a common prejudice has been that material out here is probably more pristine, more representative of the starting stuff from which everything else was made, because this material never got hot and never got close enough to the sun to be fully cooked. And so any material that gets in a comet out here is likely to be more representative of the overall starting material from which everything else was made. In addition, comets spend most of their time out here and they stay very cold, and so one would hope that after the material got in the comet, it's kept pristine. If all the material on the Earth was originally interstellar material too, but the Earth has processed it all so that there are no rocks on the planet that date back to the formation of the Earth. So we can't learn much about the starting materials on the basis of what we see now. But in the case of a comet, where you don't have all these processes happening, these materials could potentially survive. And then, of course, there's another interest in comets, which is there's a common idea that people are working on, including we working on in the astrochemistry lab here at Ames, the idea that you can make organics by many processes in the interstellar medium. Some of these organics can get into comets where they can be preserved and then ultimately dropped on the surfaces of planets, and that these organics can then maybe play some role in getting life started and in its evolution. So comets, for all these reasons, are objects that we would really like to get samples from. Okay, let's talk a little bit about the comet we went to. We went to Wild 2. Prior to 1974, Wild 2 was in an orbit where at its most distance from the Sun, it was outside the orbit of Uranus, and at its closest, it came right down to where Jupiter is. This is not a stable orbit. The comet could not have been in this orbit for that long. Presumably, it was originally out here in the Kuiper Belt and had an encounter or a series of encounters that somehow had it have a close pass with Jupiter, which then captured it into this orbit. Well, on September 10th of 1974, it had another encounter with Jupiter. It almost struck it, missed by just enough to be flung into a new orbit, which is now this inner red one. So the current orbit, Wild 2, is in at its most distance from the Sun. It's at Jupiter's orbit. And at its closest, it's actually getting down close to the Earth. And it's also in the ecliptic plane. So its orbit is very favorable energetically for us to get to. So it's actually a great target, was a great target for Stardust for two reasons. One is just for practical reasons. It's easier to get to than most comets. And then as a second reason, this is a comet that has, as far as we know, not been very close to the Sun until 1974. So it has not made a lot of passages near the Sun, unlike Halley, which has made potentially hundreds of passes near the Sun. So we may be seeing a much more original comet that hasn't suffered so much loss due to loss of volatiles due to solar warming. Now this orbit here obviously is still not stable, and so one of Wild 2's ultimate fates will be to run into Jupiter or be flung into yet another orbit by Jupiter. So this comet will probably sort of be like a pachinko ball in the solar system for a while, and at some point it will be either completely ejected or destroyed. Okay, now if we zoom in, this is Wild 2's current orbit. This is the Earth's orbit. This just shows what the spacecraft did. We launched in 1999 into an orbit where we went out and spent 2 years and came back to meet the Earth to do an Earth gravity assist, which then boosted us into this orbit so that we crossed the comet's orbit right here. When we got here the first time, the comet was over there. So we had to go around again, so there's a lot of waiting in this mission, okay? And then on the third pass out, the comet overtook us here, and we collected our sample. I'll show you how we did that. And then while the comet went back on out into the outer solar system, we went out one last time, came back in, and returned to the Earth on January 15th of 2006. So this whole trip involved launching from Florida in 1999, landing in Utah in 2006, and we traveled about 2.88 billion miles total. That comes out to an average cost of about 7 cents per mile. For those of you who are civil servants, you'll all nod your head and appreciate that this is well under the allowed travel allowance for all things governmental. However, again, in the interest of full disclosure, while that's a very cheap cost, I should point out that there are, in fact, easier ways to get from Florida to Utah. Here's one you can get on MapQuest and gives you that. And I can't vouch if this is the best route, but if you actually look at this route and compare it to what we did, Stardust's average terrestrial velocity was only 0.04 miles per hour, so maybe that's why it was so cheap. Actually, technically, I think it should be higher because I think we really got from here to here going the other way around the Earth, but anyways. Okay, I'm not going to talk a lot about the spacecraft, and in particular, since I want to talk about the samples, I'm not going to talk a whole lot about the instruments that made in situ measurements while we were at the comet, but just to point out a few relevant details, we flew by the comet at 6 kilometers a second, so something like Mach 20. So one of our concerns was that if we run into anything substantially large, something the size of a marble or bigger, could potentially utterly destroy the spacecraft. So the front edges of everything were protected by Whipple shields, which are a series of basically bulletproof vests and thin metal plates. And these were designed so that they could stop anything up to about a centimeter. And the front panel here was instrumented with an impact detector so we could tell what was hitting us during the flight. And at least we have evidence that we were struck probably by at least 6 things big enough that they could have taken us out if we had not put these shields on. So the shields were a good idea. However, none of these larger particles actually hit the collector. So this is the main thing I want to dwell on here. The collector, and I'll show you an image of the real thing here in a second, is basically a kind of tennis racket that sticks up that contains aerogel, which is the magic material we use to collect these hypervelocity impacts into. And so this thing was just stuck up into the stream during the flyby and then all folded up, and then this part was delivered back to the surface of the Earth. Okay, the collector material is aerogel, which is basically fluffy glass. Here's an electron microscope image of it. It's sort of like an extremely open sponge-like structure, and all of this is, if it were made perfectly, would be just pure SiO2 glass. I have a piece here in my pocket after the talk. If people want to come up and look at it a little more carefully, they can. It kind of reminds one of solid smoke. In fact, you can make the densities of these things so low that in fact, the mass of the air that's in the interstitial areas here is a non-trivial fraction of the mass of the volume. And so we basically, our collector was a tray that had 137 of these little tiles inserted in it. And so when a particle hits aerogel at a hypervelocity, it's a little bit like shooting a BB into styrofoam. The particle doesn't have to stop instantly. It can slow down a little more gradually. So if you fire a particle at 6 kilometers a second into a metal plate, there's an explosion, a flash, a bang. You make this pit, and then maybe there'll be a little bit of material left behind in this pit, but a lot of it will be modified, and most of it will be vaporized and lost. But if you fire into aerogel, the particle can slow down more gradually, and more of the material can survive. And I think you all have an intuitive sense for this. And if I told you you're in a bus and the brakes are out, and I ask you, let's take a vote, who wants to stop the bus by running into a big pile of pillows? Who wants to stop the bus by running into a sound wall? And I think everybody's going to say, I go for the pillows, right? So, and in fact, as you go lower and lower density aerogel, the particle takes longer and longer to slow down, and then it suffers less and less damage. Now, in these particular shots, these are test shots done with little single mineral grains. You see that what we get is what we call a carrot track. It's shaped kind of like a carrot. There's a long hollowed out tube, and then at the very end of this tube will be the terminal particle, the thing that made the track. However, if you fire a particle into this which is much more fragile so that when it hits the aerogel it breaks up, you can get different shapes. And I'll show you, when we look at the actual tracks made by the Comet material, you'll see that some of them actually are long, thin tracks like this, but many of them are not. And that actually gives you a big clue right away about the nature of the grains. Okay, we launched on February 7th of 1999. We had the Comet encounter January 2nd, 2004, which meant when I went down to JPL to deal with the encounter stuff, I had to make sure I got a hotel on the right side of the Rose Bowl parade route. Otherwise, I would have had all sorts of troubles getting back and forth during the rehearsals. I'm not going to talk tons about the structure of the nucleus, but we'll look at some pictures quickly. The main point I want to make is that when we got there, we see all sorts of geoforms here, if that's the right word to use, that are unique to this object, that are structures that we have never seen in anything else in the solar system. And these are probably largely due to the fact that we're looking at a comet that's losing material actively as a process of outgassing, and has been doing so only for a little time. So not only does this not look like other objects that we're maybe familiar with, like asteroids, surfaces of planets, but it doesn't look like other comets either. And in fact, I think I have a picture that demonstrates that. Here's Vil-2 compared to several asteroids at roughly the same size scales, and you can see they look very much different. Your eyeball tells you initially that some of these pits are craters, okay, but in fact their morphologies are all wrong. If you look at a crater on an asteroid, you see it has a rounded bottom, it has a raised lip. They're generally fairly round. Here you see they can have all kinds of odd shapes. They have no lip, they have vertical cliff edges, and a completely flat floor. So this is not an impact crater, or if it is, it's a highly modified one. Also, if you compare it to other comets, you can see that it's very much different. There's a lot more surface relief here than there are in these. And I think the reason for that is these are comets that have gone close to the sun many, many times. And so all their outer materials have been lost, and you're seeing a secondary surface associated with that loss. Whereas in Stardust, we still have little bits of the original surface, and then we've got areas which, for example, the bottom of this depression here is quite flat and may in fact be what ultimately will be the surface like this in these objects. So I would love to go back to Stardust at a later date, give it another couple passages around the sun and see how things have changed. So I think that the main reason why this surface is unique is because of that. Okay, we're ready for the 3D thing. So you can now put on the glasses. You want the blue on the over your right eye, and you'll get a better effect than I will because I'm not quite on axis. But so just to point out a couple of things, most of these pits, in fact, are not simple impact craters. As you can see in this, it's clearer that the bottom of this thing is very flat and has vertical edges. In fact, there are places I'll show you where there may even be overhangs. In this image over here, there's a 3D image of the nucleus taken at a shorter exposure, so you can see the nucleus, superimposed on an image of a longer exposure where we've blocked out the nucleus so you can see where the jets are. This comet produced many, many jets of dust and gas. I think people have counted at least 23 independent jets. And one of the things to point out is, while there are many jets, they don't just come off the sunlit side of the comet. In fact, you can see one here that seems to be emanating from this shaded area. And in fact, there's one over here that's coming out of the back side. So this tells you it's about 3 by 4 by 5 kilometers. So is what this tells you. The fact that you have clear jetting activity even on the dark side is that the sublimation that's driving the jets is not caused by direct insolation of sunlight onto exposed ice at the surface. Instead, sunlight is somehow heating the surface, and that heat is penetrating deeper into the nucleus. And then there's some underground source region where the volatiles are going into the gas phase and then streaming out. And that's important for us in the sense that when we flew by the comet, most of the particles we collected came from a few of these jets. And since these jets must have a deeper origin, it tells us that we're sampling not the surface of the comet necessarily, but some lower portion of the nucleus that's at depth.
Excuse me, you're saying then that the comet is not rotating at all?
Well, it probably is. I would be amazed if it isn't, but our entire flyby set of images spans about 10 minutes. So if this thing had a rotation period of hours to days, we would have no evidence in our images of what it is. So for all intents and purposes, for the flyby, it wasn't rotating, but it probably does. I'd be amazed if it doesn't. From ground-based data, people have made several models to predict what the axis would be and the period, but we couldn't verify any of that from our stuff. Okay, here's just another picture from another angle. Here's one of these depressions. One of the things I find intriguing about this is down in the middle of this depression, there's a pinnacle that sticks up. You can see here, you can see its shadow on the back wall there. This thing is something like, it has to be at least about 100 meters high, and at the top it's not a whole lot wider than a smokestack. So how you get something like that, I don't know. But the comet has many, many surface features like this. Are people getting the 3D effect okay? Sometimes it's easier than others depending on the projector. Also, you see places like here where it looks like along this vertical cliff things have slumped down, like maybe it had been undermined and then the whole thing had slumped down. Here's a close-up of that one area I pointed out earlier where you can see it has these very steep cliffs and a flat bottom. In fact, one of the things I find very intriguing is there are areas where it looks like there's almost a crust, which is a little tougher than the rest, that may have been the original surface. And here's an area where it looks like that. And you see this area, and then there's this depression, and there's a depression behind. It's not clear, and we don't have any images that can tell us, but it almost looks like these are overhanging this depression. And in fact, for all I know, this is an arch that it connects under there. So there's some very strange landforms here. And the vast majority of these are probably associated with evolution due to the loss of the volatiles, not from impacts or some other activity. Okay, this one's a little tougher to get, and so good luck with it. But you can see here there's a long spine or a ridge. My guess is that the way you form something like this is you have two of those depressions, and if the walls are vaporizing away, they just, the thing grows until they meet. And then when you get to a point where even this is gone, then you'll have a much smoother surface here, and you'll start looking more Halley-like. The other thing that's intriguing in this picture is there's one little patch right here that has a much higher albedo. I'm not sure what to make of that. Okay, you don't need the 3D glasses for a moment here. During the flyby, we had a dust flux monitor that could tell us if things were hitting us, and in fact they were. At the time, this graph here shows time on this axis, the number of things hitting us on this axis, and the size of things hitting us on this axis. So at the closest approach, we were getting pounded by things, and then it dropped off, and then we got pounded by things again. Probably what was happening here is we were running through 2 or 3 of these jets, and that's what we were collecting the particles from largely, was a modest number of these jets. So one of the caveats I should point out here is that it's not entirely clear, if comets are heterogeneous, it's not entirely clear that the material we got necessarily represents the nucleus as a whole. And then up at this size range is some of the biggest particles. These are even smaller than the ones that could penetrate into the Whipple shield, so we got hit by some things that are even bigger than this. let's see, what else can I say about this? I won't get into too much detail, but if you actually look at the fine details of the timing of the particles hitting us here, it was very odd. The number of impacts did not simply rise up uniformly and then fall off uniformly. Instead, it was extremely stochastic. There are periods where for a tenth of a second, we would be hit by maybe 100 particles, and then for the next 9/10 of a second, we would be hit by 0 particles, and then in the next tenth of a second, we'd be hit by 50 particles. And the reason for that is probably this. When we were flying through we didn't get any particles unless we were in a jet. But when we were in a jet, we only got particles some of the time, and that must be because jets, when they're shooting out their particles, shoot out largish grains that are aggregates of smaller grains. And as that grain floats out, it comes apart. Maybe it's losing ice or something else. And so when we're flying through the jet, we won't see anything unless we're in a jet. But if we're in a jet, we won't see anything unless we get hit by one of these shotgun blasts that's traveling outwards. And so you'll get 0 particles or you'll get a bunch. So, and that seems to be consistent with the timing we see. So that was actually a hint early on that the grains we were going to get back might not be nice, big, monolithic chunks of things, but might in fact be aggregates of smaller things. And you'll see that ended up being quite true. Whoops, I went backwards. Okay, after we did the collection onto the aerogel collector, it was folded up against the arm, and then the arm was folded into the return capsule, and then the clamshell was closed. And then this part was ejected with a slight spin on it when it got targeted on the Earth's limb a year and a half later or so. And it came back to the Utah Test and Training Range, which is a federal sort of military preserve here near the Great Lakes in northwest Utah. This is a place that has many advantages and a few disadvantages for bringing things back to the Earth. It's highly instrumented airspace. Things don't move through the air there without being measured. And you have very flat terrain, as you can see in this picture, so you have little vegetation or other things to lose sight of the capsule on when you're hunting for it. A lot of trained personnel around, and then very few people to drop things on. Since there are very few people, for example, you don't have to worry about getting there in a rush because someone may steal the hubcaps, before you get there. Some disadvantages are that they call these dry lakes, but of course that's an oxymoron. Sometimes they actually are lakes, and they tend to be lakes in the winter, which is when we came back. And so one of our enormous concerns was what the weather would be like at the time of the return. And it actually came back in a snowstorm, but fortunately it kind of came down in a hole in the storm. And there was no standing water where it came down, but, and it's not so obvious in this picture, this stuff is some of the worst cloying mud you can imagine. It's terrible stuff. It took me hours to clean my boots off after we fetched this thing. However, we were fortunate, and I was really worried about we were going to get this capsule with its 1,000 10-micron comet grains, and then we're going to drop it in mud, and then take it to a clean room so we can open it up. Well, how clean is a clean room going to be after that? But it turns out the heat shield did us a favor. Not only did it perform extremely well in terms of getting the capsule to the atmosphere without burning up, but by the time it was done, the capsule was covered with a layer of soot. So when this thing came down and hit the ground, instead of mud sticking to it, the mud pulled part of that charcoal layer off the shield. And so you can in fact see an area where the shield has been sort of wiped clean here. And so it came down in a crosswind, so it landed on its nose, and then it bounced in the air and landed on its back, and then it bounced in the air and it landed on its side, and then it bounced in the air and it landed on its side again, and then it rolled like a quarter on a tabletop for about 30 meters, and then it finally laid on its side and landed. When we were preparing for the mission, we wanted to know how is this thing most likely going to land, because we have these issues about where we put the vents and all this kind of stuff. So we got a rental truck and made a mock-up of this and went out in the desert and threw it out of the back of the truck as we drove around at different speeds. We didn't tell the rental guys this, by the way. And discovered that, because we wanted to know, will it land on its nose, will it land on its side, or will it land on its back? Okay, and the answer is yes, it will in fact land on one of those. And in fact, the most alarming test was one where we threw it out the back and it did a couple of really nasty-looking bounces and then rolled across the desert. Well, that's what happened. Fortunately, since we did not have standing water, nothing really got into the capsule at all during any of this, and we've found no indications whatsoever. This was one of the tasks I had a large responsibility in. No indication whatsoever that anything associated with a landing contaminated the sample in any way, including any of this ablation that happened during this phase of the return. So this all went picture perfect. Okay, we then took it back to a temporary clean room where we took the two parts of the heat shield apart, took out the sample collector canister, put them all in sealed boxes. We got a little bit of sleep, and then the National Air Guard gave us a flight down to JSC where we opened this up in a special clean room built specifically for the sample. And we actually knew within a modest number of minutes, actually, that we had been successful because some of the impacts were sufficiently big you could see them with the naked eye. We'd been expecting that most of our sample would be in grains that are smaller than 100 microns, and that you wouldn't even know they were there until you looked with a microscope. But in fact, some of them were big enough that it was obvious right away we had comet sample. So these are two cartoons, but they both make serious points. One is when your entire sample is 1,000 10-micron grains, and a 10-micron grain is like a nanogram, a billionth of a gram, you can only manipulate and study them in the most cleanest of conditions. One good sneeze, and that's the end of it if you do it in the wrong place and time. And the other is that when you want to interact with other people about the sample, you have to spend a certain amount of time educating them to the realities of the sample so that they don't do silly things. Okay, so here's some close-ups of the return. Here's a part of the tray, and you can see a sort of halo here and here. These are two of the biggest impacts, and you can actually just see them with the naked eye. This is what one of these things looks like. If you pull the cell out and look at it from the side, you can see the top part of the track. This is a microscope image, close-up image of a couple of tracks. So here you can see, here's a track that looks kind of like those ones I showed you earlier, a nice thin carrot track. So this has probably got a terminal particle at the end that's a nice hard mineral or something. But many of the tracks look like this. They have a very narrow entrance aperture, then a great big bulb, and then a series of roots that come out the bottom. So this is not a carrot, this is, I don't know, ginseng or something. And in fact, you do find terminal particles at the end of this, but there's also material all up and down this track. So this is a strong indication that many of the particles that hit were aggregates of smaller grains, and the minute they hit, they just came unglued, and particles went everywhere. So that's nice in that it's informative about the nature of the particles, but as you may already be appreciating, this is something of an analytical nightmare. You were already talking about trying to measure important things from a nanogram of material, but now you've taken that nanogram material and you spread it out over a centimeter, okay? So this is a major challenge for us. In addition to things hitting the aerogel, they could of course also hit the frame and the aluminum foils that hold the aerogel in place, and so we also get some of these craters. And a surprisingly large number of these craters still contain material in them, and in fact we can study some of that, and I'll show you some data even from those. Okay, let's go back to the 3D glasses for a second. I'm not going to spend a lot of time talking about the craters because obviously they cause more effects on the original material, but many of the craters have this sort of classic shape that you get when you fire things into metal at these velocities, kind of a nice rounded bowl with a curled back metal lip, and there is some material in these things. But there are a few that are really odd, that are quite different. So I'm going to go to it. Now the next slide is a blow-up of this thing here. Okay, this is clearly an impact from something that wasn't a single grain that made a nice round pit. In fact, it must have been a composite grain of multiple things. And in fact, if you go in here and you look at the residue that's left behind, you find out the composition in each of these pits is not the same, that the material in the grain that was this part of the aggregate is different from the material that was this one, that was different from the one in this one. So not only were the grains we got consisting of, many of the grains we got consisted of aggregates of smaller things, but those smaller things aren't all the same thing, okay? We don't have, I'm trying to think of what's a good example here. We don't have clusters of kicks, okay? We have clusters of tricks. Okay, the subgrains are not all the same thing, they're different. Okay, now this is a 3D one that I don't know if this will work for you or not. This is actually a track, but since you're trying to image something with very low contrast, because you've got aerogel, which is almost nothing, and next to air, which is also almost nothing, I have a hard time getting the full 3D perspective on this, but you can get a little bit of a sense of it. So the penetration hole is up here at the front surface, and it's very small. It's about the diameter of the particle itself. Then it widens out as you get into this explosion region, and then you have these other tracks that come down that have the larger, tougher grains. Okay, I think that's the end of it for the 3D. Like I say, if it's a fashion statement, you want to keep them on, fine. Okay, so here's a blow-up of an example track. Again, the small hole at the front, this large bulb where the particle breaks up and many smaller things come to a halt, and then bigger grains that come down here. And so if you go to the end of these tracks, you find these terminal particles. And so these tend to be large single mineral grains. And then up here, there's a whole mess of stuff that's been busted up into lots and lots of pieces. Okay, how do you deal with something like that? Well, Andrew Westphal and his crowd up at Berkeley came up with a technique of extracting what we call keystones. You basically use a computer to control a micromanipulator and a little needle, and you just poke away, and you can poke out a wedge around the particle track, stick a little micro pickle fork in it, and extract that. And so now you can pull this thing out, and then you can either make measurements in situ. You can measure the material while it sits in the aerogel if the aerogel doesn't cause you a problem. Or you can use micromanipulators and go in and try to tease out individual particles and then study those. Okay, and micrometeoriticists are kind of a strange crowd. If you go to most people and you say, I'd like you to make a measurement and I'm going to give you a nanogram of material, they'll immediately scream, what are you, crazy? You can't do anything with a nanogram. Well, if you give this crowd a nanogram, a lot of the time they'll say, well, that's nice, but it's kind of thick. I can't get my beam through it. Would you mind slicing it up into 100 slices? So over the years, we perfected a bunch of techniques to do precisely this. And so a lot of the data I'll show you will actually be not from particles, but from thin sections of particles where we've taken a particle and just sliced it up like it's bologna. And you'll be looking at just one of the slices. Okay, I'm going to give a sort of brief overview of the results with an emphasis on the organics. I point out there was a special issue of Science in 2006 where we gave all our original preliminary results, and then there's a subsequent special issue in Meteoritics and Planetary Science where we go into much more detail, and I believe there's another issue of Meteoritics coming out in the March issue, so any day now, that has even more. And of course, since this is a sample return mission, this is not going to be the end of the papers. The papers will just keep coming in perpetuity here. Okay, so just to show you that there is some progress going on in science, this is a woodcut of Comet Donati from 1858. I don't know what the resolution of a woodcut is, okay, but this tail is presumably a couple 100 million kilometers long. Okay, this background here is the interatomic spacings of a cometary mineral grain. So these spacings are a couple of angstroms. Okay, so this is an increase in spatial resolution of something like a factor of, well, at least 10 to the 15th. Okay, so what are some of the things we found? Well, one of the things that surprised at least some people a lot, and certainly surprised all of us at least a little, was what a zoo of minerals we found. If you go through the particles, you find lots of minerals like forsterite, which is an olivine, enstatite, which is a pyroxene. These are really common minerals in normal meteorites. So in some ways, that's not so surprising. But these are well-crystallized silicates. And a lot of people thought, well, if comets are made of interstellar stuff that's just come in and hasn't been affected, all our telescopic data tell us that most of the silicates in the interstellar medium are amorphous. They're like glass. They're not nice crystals. But these are all nice crystals. Okay, we also find iron-nickel sulfides. These are quite common in meteorites as well. But then we started finding things that were a little more flabbergasting. Anorthite and diopside are minerals you do find in meteorites, but they're not super abundant. And these are very high-temperature minerals. You don't make these at low temperatures. And in fact, we then found this little thing, a vanadium titanium nitride mineral. We had to go to the books to find out what it's even called. It's called osbornite. Okay. Well, it turns out if you go to the modelers and you ask them if you take a gas of solar composition, if you took the entire solar system and vaporized it, and then you let it cool off and asked what condenses first, that's one of the first things that comes out. Okay. So this suggests that the comet contains materials that didn't just drift in gently from the cold interstellar medium and get in a cold comet and stay cold until they were delivered to Stardust collector. Instead, we have materials in here that were formed in the hottest regions of the solar nebula. So this idea that stuff came in from outside, got in a comet, and that's what made the comet it can't be right. So this was a real shock to a lot of folks. Also, this is a great demonstration of this issue of aggregate particles and complexity. Here's a grain that came into the aerogel from this direction, and this big giant iron-nickel sulfide grain basically acted as a blast shield and protected all this fragile stuff from being busted up in the track. And then behind it, there's a nice enstatite grain, and then behind that, there's a really fine mixture of all kinds of little things, and if you add up all their elements, it's roughly a solar composition. So in other words, if you took the solar system and chopped it up as finely as you could, it would have this composition right here. And this is all cheek by jowl. So this stuff is all together. It couldn't possibly have formed in the same place, couldn't have formed at the same time, but it somehow they've resided next to each other for quite a long time, and apparently happily so. So this tells you that the cometary material is really quite complex and that very little processing happened on the parent body. If the comet had gotten hot or really wet or any of these other things, these guys would have reacted with each other. Okay, so this is a problem for us. One of the obvious questions you'd like to ask from the sample is, well, okay, what is the composition of a comet? How many atoms of carbon are there relative to atoms of silicon and so on? And this is turning out to be a really difficult problem. Here's an example of the problem. These are maps of a track taken in X-ray fluorescence. So we shine X-rays in, we get various elements to light up, and you can make a map of where they are. And so here's where all the iron in the track is. So you find out the iron is spread out along the whole track, and then there's a lot of it in the terminal particle. Well, where's the nickel? Nickel usually follows the iron. Well, more or less it does, although there's clearly a phase here that's got iron and no nickel, so it's variable within the particle. Well, here's the zinc. Oh, okay, what's with the zinc? Zinc only apparently resides on the north side of a particle, I guess. Okay, and then the chromium, well, it doesn't come off in the track. It just wants to hang out in the terminal particles. Okay, so this is what this tells you is for any given impact, you have a fractionation of the elements along the track. If you can't add up everything associated with the track, you don't know what the particle had. So analytically, this is a challenge. And then to make it worse, this particle is a zoo, okay? Okay, well, you go to the next particle and you find out, well, it's a different zoo. And one's the Philadelphia Zoo, the next one's a New York Zoo or whatever. That you get similar behavior, but the actual ultimate distribution and abundance of the elements is different. So what thanks to this particular particle has way more than its share of zinc for solar composition. But you look at other particles that have no zinc, okay? So in the end, if you average these together, our conclusion so far is the comet grains, as near as we can tell, look basically like they're solar, with possibly an augmentation of some of the more volatile elements, which may make some sense if you kept them cold in a comet, as opposed to, let's say, a meteorite, which comes from an asteroid that got warmer. But this is turning out to be a real problem. We actually did a calculation where we sort of demonstrated that if we could make this measurement on every particle we had, it still wasn't clear whether the statistics would be good enough to totally say what the composition of a comet is. Okay, another thing is that since a lot of people had this idea that a comet was made up of interstellar stuff that comes in, gets in the comet, nothing else happens to it, a lot of people anticipated that cometary material would be incredibly rich in circumstellar and interstellar grains, so things that predate the solar system. And you can recognize these materials often because they have non-solar isotopic ratios. So a lot of people are expecting that we would see a lot of material that would have totally wacky isotope ratios in many of their main elements. And it turns out this is not totally true. Here is an impact into a foil that was a particle was big enough to actually punch through the foil. And some residue from the original comet was found here on the edge. And so someone went and used an ion probe to make an isotope map of this area. So in this map, they're looking at the oxygen 16, 17, and 18 ratios. And on this color map, anything that's sort of greenish-gray has the exact same isotopic ratios of anything we would find in the normal solar system material. So, for example, anything on the Earth would look, greenish-grayish here. And you go through this and you find out, well, the vast majority of this particle looks totally normal, of this material looks totally normal, but there is one particle which is completely wacky. Okay, it's got way too much oxygen 17. And so if you look at nucleosynthetic models and rare meteorite grains, you find out that it falls in this part of the plot, and that this is a part that's usually associated with AGB or red giant stars. Okay, so this little blob here is a particle that was shot out of a dying star at a time before our solar system even had formed. Okay, it wasn't even a gleam in some dense cloud's eye, right? And drifted around, ultimately got in the dense cloud, got incorporated into the solar nebula, ended up in the comet, managed to survive slamming into the aerogel, came back, we managed to find it, okay, and we measured it. But it's only this one little grain, okay? It's not all of them. And in fact, the number of grains we found that fall in this category is quite modest. And so the statistics are still a bit low, but it's clear that this comet did not contain an overabundance compared to what we see in meteorites of these grains. And it may even have an underabundance. So now this is really odd. We're making an object in the outer solar nebula, and yet it has less material from outside the nebula than stuff that's deeper in. Okay, this is a real puzzle. Also, if all the stuff that was in the comet were interstellar grains, we would expect them to be, on average, about this size, because that's what telescopic data tells us is the average size of interstellar grains. And as I mentioned earlier, most of it should be amorphous silicates. Okay, well, instead we find things like this. This is a grain that's 2 orders of magnitude too big, and oh, by the way, it looks like it's been melted. Okay, and it's quite crystalline. So all of this stuff is telling you that the cometary particles had a much richer history than I think we naively would have expected originally. A lot of this is pointing to the necessity for a lot of mixing in the solar nebula. Okay, we think comets formed out here. Some people's old model would say stuff to get in comets comes in from here, parks in the comet, end of story. But we're clearly seeing things that were formed down here. So it must have been that things came in. Some of the things got into comets right away, but some of them just said, never mind, I'm going to go on down here, and then just changed their mind and came back. Okay, so there had been mixing on almost every scale in the solar nebula. And this all had to happen before the comet formed. In fact, that had happened before the subgrains formed. Okay, so this is telling us a lot about solar system chronology. It's telling you that the early solar nebula was some kind of giant washing machine or something. Okay, now let's get into the organics. Now, I've talked a lot about hot minerals. Now I'm going to show you organics, and I'm going to show you that not everything got hot before it got to the comet. So while some things went all the way down in and then came all the way back out, a lot of things didn't do that trip down, because if they did, they would have been destroyed. So some things did come down, get in the comet, and not go any closer. And here are a bunch of techniques that we use to study the organics. Before you get too nervous, I'll tell you there will be no test on these. And I'm not going to show you data from all these techniques. However, if you want to be a little nervous, I'm going to tell you that I will show you some data from some of these techniques. Okay, the organics tell some stories that are basically compatible with the silicates. One is that they're present, and like the silicates, they're very diverse and they're very heterogeneous. Okay, so they're heterogeneous both spatially and compositionally. So this is a corner of that image I showed you earlier that had that big iron sulfide grain, and this is some of that fine grain material behind. And this is an image taken with energy electron loss technique. So things that look white are rich in light elements like carbon. Okay, so here's some organics, and they're clearly not spatially uniform. They're not just evenly slathered on everything. They're in lumps and bumps. And this particular lump right here that looks a little bit like a donut when you zoom in on it actually contains a substantial excess of nitrogen-15 relative to nitrogen-14. So this is, we know, is not contamination. This is an interstellar grain. This thing predates the solar system because it has non-solar isotopic ratios. Also, if you look at them, you can see, again, here's a map made with an ion probe showing where the carbon is. This is one of those slices I was talking about. So here's a bologna slice that's got, I don't know, a picogram of material in it. And you can see the carbon is not uniformly distributed, the nitrogen is not uniformly distributed. The two are correlated with each other spatially, but the ratio of them varies enormously. Here you can look, these are all particles from the same track. So these are all part of the same original particle that whacked into the collector. And they have carbon to nitrogen ratios that range from essentially 0 all the way up to 200. Okay, so you have things that are dominated completely by nitrogen and things that are dominated completely by carbon and everything in between. Okay, this is not what you see from any kind of normal equilibrium chemistry. Okay, well, what are these organics? Well, we're still fussing with that. When the whole particle is a nanogram and then only a fraction of that's the carbon, and then you vaporize it and spread it along a track, obviously we have some difficulty getting into too many of the details. But one of the things that is clearly true is that polycyclic aromatic hydrocarbons are present. So these are these sort of molecules that consist of hexagons of carbon with hydrogen sticking out of their edge. Most of you are familiar with this in the form of candle soot, stuff in your tailpipe, or if you barbecue the way I do, you make a lot of pHs. Okay, and we find two patterns of pHs. There's some where if you look at the particles, you see this enormous distribution where there's a peak at almost every mass. So we're making, again, a really wild and diverse group of things. But in other areas, especially if you look up higher in the bulb, you sometimes see a very sparse distribution of lightweight pHs. And it turns out you can reproduce this pattern if when you make this, the way this measurement is done is a laser desorption mass spectroscopy. You fire a laser at the sample and you try to gently lift particles, molecules off the surface. Then you fire a more robust laser through and ionize the molecules you're interested in measuring, and then you sweep those into a mass spec. Well, if you take that first laser and instead of trying to gently lift the molecules, you just crank up the knob, you go to 11, and you totally pound on the aerogel so you're punching holes in it, you can reproduce this pattern. And so it looks like you can basically make these pHs from the original aerogel material if you simply heat it, flash heat it. And flash heating is part of what happens when you impact a particle into it. So these distributions are probably associated with pHs that are actually from the comet, although the population may have been somewhat modified by the impact process. These pHs are probably secondary and are produced by the impact process. And whether the original carbon in these pHs came from the comet or comes from the aerogels is kind of an open issue. But in any event, these molecules probably didn't exist on the comet. They were made in the aerogel. Okay, another technique we use is Xray Absorption near-edge spectroscopy, or XANES. And this is a handy technique this is an example of a technique that wasn't very robust when we launched the spacecraft, but ended up being a real workhorse for us when we got back. The basic idea here is you take an X-ray image of your particle at some energy, bump the energy up slightly, and take another image, bump it up a little more, take another image until you have a data cube. And so, and in these dimensions you have images, and in the vertical dimension you have an X-ray spectrum, an energy spectrum. So then what you look for is absorption features. So what's going on in these absorption features? So for example, this one here is we've reached an energy where we can the X-ray has just enough energy to take an inner electron from carbon and just fling it out of the atom. And so as you go through this energy range, you are knocking electrons out of the atom, and so the more carbon you have, the more electrons are getting knocked out, the bigger this absorption feature is. So the area of this peak is a measure of the total amount of carbon in the beam. And you go to another energy, this is an energy sufficient to knock an inner electron out of nitrogen, and that's oxygen. So if you measure these peaks, you can then come up with a carbon-oxygen-nitrogen ratio. And so in fact, when we look at the Stardust stuff, here's for this particular particle here, we have this carbon-oxygen-nitrogen ratio, and that's compared to primitive meteorite, Murchison, and they're somewhat similar, but you notice that the Stardust materials have almost twice as much oxygen and twice as much nitrogen relative to carbon. These are very oxygen, nitrogen rich. Okay, that implies these organics are fairly primitive. If you cook an organic, you tend to drive the oxygen and nitrogen out and get more and more carbon rich. So in addition, you can actually, if you have good energy resolution, you can get even fancier. Just when you get near the edge where you can fling an electron out of the atom, you get to a point where you can fling it out of the atom but into a molecular orbital. And so the energy structure of the absorption right on that edge can tell you not just that you're dealing with a carbon atom, but it can tell you what kind of bond, chemical bond the carbon atom has. Is it aromatic? Is it aliphatic? Is it bonded to a nitrogen? And then since you can look at the nitrogen edge too, you can look for consistency. So if you see a band here that says, oh, maybe we have a C triple bonded to an N, you can go to the nitrogen edge and make sure you see, the N triply bonded to a C. It's got, has to work that way. And so this allows you to say something about the chemistry. And what we find is that the chemistry of the organics is just like everything else, wilder than what we see in meteorites. Okay, many of the particles have a spectrum that looks a bit like this. It's got a lot of aromatics and a bunch of other bumps and wiggles. And if you look at this in detail, it looks superficially, at least, like the kind of organics that are common in meteorites. Except we still have this extra oxygen and nitrogen. It's still about a factor too high. But we also see particles like this that have incredibly simple chemistry. There's a very few different kinds of bonds here. And the oxygen is outrageously abundant. It's almost half the abundance of carbon. Okay, it's hard to make a molecule with this much oxygen in it. And in fact, is what the kinds of structures I can draw that have this kind of a composition are things like polyoxymethylene. This is where you just take formaldehyde atoms and you just stick them end to end, end to end, end to end. So this is a very simple chemistry. And this is the kind of chemistry we can reproduce in a lab here at the astrochemistry lab by irradiating astrophysical ices. So you basically, zap an ice with UV photons, bust up the molecules, and remake new ones. And you don't see this stuff in meteorites. That's completely new. So here's a series of these things to show you how much they vary from particle to particle. The ones up here look superficially like meteoritic material. This stuff is completely different. And if you plot all of these points on a nitrogen to carbon, oxygen to carbon thing, you find out, well, most meteorites fall here. A few rare primitive meteorites fall here. We fall here. Okay. So these things with a lot of oxygen and nitrogen should be much more labile, much less robust, less able to take the rough and tumble of everyday life in the solar nebula. So they probably have not been radically changed over time. And in fact, we see other evidence that these particles are labile. One of them is, here's a particle in thin section where we've sliced it up in bologna as a bologna slice after we embedded it in epoxy. And when we take the Zane's image of it, we find out that, well, here's the particle, but there's extra material out here that looked like it dissolved from the particle and flowed out into the aerogel. So this is something there's an organic present that's soluble in epoxy. Okay, we never see this in meteorites, okay, whatever this stuff is. Also, here's an image of a track. So this is the visible image of a track. You can see it's a nice thin pencil. But if you take IR absorption maps of this, you find, and you ratio out the signal due to the aerogel, you find out that you have a lot of excess material right here, which corresponds to CH2 groups. And you can make a map of their abundance, and you find out that there's a lot of excess organic here. And it's not just constrained to be inside the track. It's actually in a volume well outside the track. So it's clear that when this particle hit, it contained an organic component that vaporized, diffused into the aerogel, and recondensed. So this is another one of our analytical nightmares. Okay, before you were asking me to measure nanograms at a time. Now you want me to measure individual atoms spread out over a big area. So one of the problems I think we're going to have with Stardust is we probably never will be able to give a very good number for what is the abundance of the organics relative to the minerals, because the two fractionate during the impact, and it's very hard to track the two down completely. Okay, another one, which is now we're getting even more speculative. There was a possibility when we flew through the coma that we also collected molecules, that there were some things that were just in the gas phase that ran into the aerogel, and maybe they made their trip back. So a number of people, including Jason Dwork and Danny Glavin at Goddard, have looked at pieces of aerogel that have no tracks in them. They were just aerogel exposed to the comet, but have no tracks that are visible in them, and looked for various kinds of molecules in them. And what they found is that the exposed tiles tend to show big excesses in methyl and ethylamine, which are amino acid precursors, and maybe even show a bit of an excess in glycine, the simplest amino acid. And so there's some evidence that maybe we in fact did get a molecular return in that regard, but it's very hard to track down because it's even more diffuse than the stuff that got vaporized out of the tracks. So we're still working on that one. Okay, and then of course one of the things which some of you may be worried about, and and it'd be perfectly justified. I'm telling you things about organic materials that were brought back from the comet, but I'm talking about nanograms of sample. We live in a world completely, surrounded by organics. How do I know everything I'm measuring isn't just, clean room personnel spit, And that's a good question. In fact, for almost every measurement my organics team made on comet samples, we also made measurements on various kinds of controls and other materials to try to confirm that we weren't getting dominated by organics from contaminants. So for example, for every comet sample some of my people measured, they also measured a sample of UTTR mud, a piece of the heat shield, a piece of the parachute on the return capsule, 5 pieces of aerogel that were made at the same time as the flight aerogel but didn't go on the flight, etc. Okay, and so in most cases that's, and also you can look for organics that are intimately associated with the mineral grains came from the comet. So in most cases you can sort it out, but when the real holy grail, the one where you don't even have to worry about all of that, is if you measure an organic and you find out it has an isotopic anomaly that has non-solar, non-terrestrial isotopic ratios, then it's got to be from the comet. It may have been modified somewhat, but it has to be from the comet because it can't be terrestrial contamination. And so in fact, if you look at the grains, you find out that while I said earlier these circumstellar grains seem to be kind of rare, interstellar grains don't seem to be all that rare. So in other words, materials that were formed in the outflows of stars, we're not finding a lot of those, but materials that could have formed in the interstellar medium and then get involved aren't that rare. So we find particles that have enrichments in deuterium relative to hydrogen, and they're not that uncommon. So far we haven't found any enrichments that are record-breaking, so the excesses are somewhat modest, nothing super extreme, but nonetheless their presence is a clear indication of interstellar material. And we also find nitrogen-15 hotspots. So while the pre-solar grains appear to be somewhat rare, the pre-solar interstellar materials are not. So the organic chemistry from the interstellar medium is shining through all of this. Okay, so a couple of high-level summaries. Most of the captured particles we got were actually weakly bound complex aggregates of smaller grains, and these smaller grains are not all the same kind of grain over and over again, but a whole host of different things. The minerals show an enormously wide compositional range, and high-temperature minerals are present, and most of them, well, the ones we can detect and identify clearly are all crystalline, not amorphous. I should add one caveat here. If amorphous silicates were present, we would have a hard time knowing because we collected them in aerogel, which is a amorphous silicate. Okay, so there's one caveat to keep in mind. Sample heterogeneity makes it difficult to obtain a representative bulk composition of the dust. Insofar as we can tell so far, it's consistent with the same kind of compositions we get from primitive meteorites with possible enrichment of these moderately volatile elements. Isotopic anomalies show the presence of pre-solar materials, but Wilt-2 is clearly not just a collection of pre-solar grains. In fact, much of the material has got a very aggressive solar history. Organics are present, and they show a greater compositional diversity than we see in meteorites and any other previous extraterrestrial material. So far, the Wilt-2 materials show no clear affinity to any specific meteorite type. Okay, they're their own beast. They don't look like any other extraterrestrial material we have. And it's clear from these results, the heterogeneity, that one, there's a great deal of mixing going on in the early solar nebula, and it happened early. It happened even before the comets formed. And comets, or at least Comet Wilt-2, are repositories of relatively unprocessed early solar system materials. So once the material got in the comet, not much happened to it after that, even though a lot of things clearly happened to the grains before they got in the comet. Okay, on the side of the organics, we see organics that are distinct from those of primitive meteorites. There's some fractions that show similarities to the kinds of materials we've seen before, but there's also some that are just completely new. They're generally very rich in oxygen and nitrogen, much more so than meteorites. At least some of the organics appear to be relatively labile because we see them creeping around in our epoxy and vaporizing in the tracks. And the distribution, both in abundance and composition of these organics, is extremely heterogeneous, both within individual particles and between separate particles. So they clearly represent an unequilibrated reservoir of materials. This is sort of further evidence that they didn't get processed much in the comet nucleus. And on the whole, the organics are more primitive in the sense of showing less evidence of subsequent processing than the bulk of organics we see in meteorites. And again, just with the minerals, they show no clear affinity to any kind of meteoritic material. And the enormous heterogeneity highlights the dangers of inferring cometary compositions on the basis of measurements of individual species. I mean, astronomers like to go and look at a comet, measure the HNO coming off of it, say something about the HNO isotopic ratio, the nitrogen isotopic ratio of the comet. Very dangerous idea, I think. Okay, now just to end, a few shameless advertisements. One is, this is a follow-on to one of my earliest slides. This is me putting away the aerogel collector after we'd removed the first 2 tiles. So here I am playing the Aerogel Guitar, okay? And I think all the stuff I've shown you and all the work that's been done to date is associated with particles removed from maybe 10 or 12 of these tiles, and we haven't even used all the material on those. Okay, so this is a repository of material which is going to get studied for decades and continue to learn about comets long after I'm around to look at them. So the money was well spent for Stardust, and it will continue to pay off into the foreseeable future. Second of all, I didn't talk about this much during the talk, but the backside of our collector, which never saw the comet, was actually popped up and exposed in space during the first 2 critical points of the first 2 orbits around the Sun at such a time and in such a manner that interstellar grains coming in from outside our solar system could have hit the backside of the collector. So we may have a collection of contemporary interstellar grains on the backside. So these would be grains that are 4.5 billion years younger, fresher than anything we brought back from the comet. And so that was not a principal part of the science for Stardust, so it was not funded to do the analysis. So we're doing it sort of on the cheap after the fact. And of course, one of the hardest things about finding the interstellar grains, or about studying the interstellar grains, is just finding them. Okay, remember that picture where I showed you that big blobby molten thing, and then I said this is the size of an interstellar grain? We're looking for the things that size now. Okay, and so the way we're doing it is by doing what the government does a lot of the time, making the citizens do it, right? The basic idea of this is, if you go to this website, you'll get all the details. But basically, you can join the group. They call themselves the Dusters, I guess, where you can go on a website, get a little bit of training, and then once you've got the training, you can go in and get a database of microscope images taken of the backside collector and scan through them looking for tracks and flagging them. And then we keep a track of these flags, and then we're now just beginning the process of going back and pulling the first few tracks to see if they actually have grains in them. And I'm not going to tell you how we know, but we have a way of testing how good people are at this. And they're remarkably good. The number of false positives they give are really low, and the number of things they miss is almost unmeasurable. And so these dusters are doing a great job for us. And I think at this point we've scanned about half of the tray, I think. And we found about 100 candidates, and we removed the first few. And as a practice, the first few we removed were ones we were pretty sure were not interstellar tracks because they kind of came in at an angle. And if you trace the angle back, you find out that they point at one of the solar panels. So probably what we're seeing there is a particle that hit a solar panel, exploded, and various bits of stuff ended up in the backside of the tray. And at least some of that material has just the right composition to be the coating they put on solar panels. So, but at least we sort of did a demonstration of proof. People can find the track, we can go and dig it out, we can find the particle, we can measure it. So the next step is, of course, to do this with a real interstellar grain. Okay, and then my last advertising slide is a look to the future. I actually get on a plane at 5 o'clock tomorrow to go fly to Washington, D.C. to make my final presentation for a concept study I'm responsible for, which is the Comet Coma rendezvous sample return mission, where we would basically go to a comet and park near the comet. Since instead of flying by at 6 kilometers a second, we'll loiter with it for almost 6 years and take pictures as it changes. And occasionally we'll go down and we will wallow in the dust that's coming out of the jet, so we'll never land, and come back absolutely filthy. Okay, and this will bring back maybe 1,000 times as much material, and it'll be material we collect at meters per second, not kilometers per second. So we'll have none of these impact-induced issues to deal with. So I'm going to be talking about that on Friday. But in addition, the next sample return mission that I'm aware of coming back is the Hayabusa mission. I'm one of the U.S. co-eyes on this. This mission's got a checkered history. It's done some amazing things. But while it was at the asteroid, it had various problems that ultimately, for reasons I'm not sure I understand, lost all of its chemical fuel. So we're coming back on an ion engine. We've got one of the 4 original gyros. The battery's frozen, so the solar panels have to be in the sun all the time. And so it's not clear whether it's going to make it all the way back. And oh, by the way, since we had this little accident at the asteroid, we lost the volatile memory, and so we don't actually even know if it got the sample or not. So, but nonetheless, in 2010, we hope to come back and drop it in Australia and find it. This is the asteroid to scale with. If you're Japanese, you maybe prefer to compare it to the Tokyo Tower. For us locally, maybe the Golden Gate Bridge is better. Hopefully you never actually see this. I can think of very few good things about seeing something like that. I guess you don't have to do your income taxes that year. But But in any event, and I think it's July 2010, the sample will come back. My plan is to be in Japan to help receive the sample, and we'll take it out, and hopefully there'll be something in there. And the nice news is, even though this mission was designed to bring back, sort of a can of rocks, we know from the Stardust mission that even if the collecting device didn't work perfectly, if even a little dust got scattered up in there and we can find it, we're getting pretty good at finding little things spread out over big areas, we can measure a lot from it. So even a really tiny sample will allow us to learn a lot. And I think Stardust is a great example, as is the Apollo program and the Antarctic Meteorite Return program. Once you have a sample in your hand, you can learn things that you're just not going to learn any other way. And so I'm looking forward to Hayabusa coming back, and I'm even more looking forward to NASA saying, yeah, maybe we should do another Comet mission where we go there and get this stuff in really pristine form. So I think that's my last slide. I'll end there and be happy to entertain any questions anybody may have.
Cynthia has to run, so I'm going to take over the questions. So if there are any questions, remember to speak into the microphone.
This is a little bit different. Are there any plans for sample return to Mars?
People have wanted to bring back samples from Mars for forever. I don't have a copy of it, but it would, I could get a good laugh by showing a plot that I've seen appear more than once, which is the time till Mars sample return, and it's always 10 years away, and it has been for decades. But yes, just as with these primitive samples, any object, whether it's a planet or otherwise, if you can bring a sample back, you can start to learn things about it that you just never learned by imaging it or whatever. I mean, one example that we're probably not going to pull off with Stardust, but we could pull off with one of these subsequent missions, and which you would certainly do on a Mars sample return, is once you have a big enough sample that you can reliably measure mineral separates and so on, you can do chronologies. You can start to date things. You can say this rock is 1 billion years old, this is 1.2 billion years old, this mineral formed before that mineral, and so on. That can give you a tremendous amount of information about the whole evolution and creation of these materials. So yeah, sure, a Mars sample return would be great.
We're also talking about other moons in the solar system. Do you have any data on that?
Most of the moons that I'm aware of that have gotten attention are people are interested in things like Europa, where there's also this issue of life and so on. Sample return from some of these objects is a lot more difficult because if it's an ice, then it's much harder to get back. I mean, if you collect an ice, if you don't keep it at 100 degrees Kelvin the whole way back, which is technically a complicated thing to do, then what you won't get back won't be ice, it'll be a bottle of water or something, okay? And while you could still learn stuff from that, you have this problem that once your ice is allowed to melt, then you're doing the same thing you do in your chemistry lab when you pour things back and forth. Chemistry can happen in there that post-dates your collection of the ice. So there are people who talk about that kind of a return, but I mean, when I pitched these proposals to NASA to do the next generation Comet sample return, it was my feeling that it's too aggressive at this point to have a volatile return. So this is what the mission I'm pitching has is a much gentler refractory return, and then we'll have onboard in situ instruments that can measure volatiles in the form of mass spectra of the gases that are coming off and so on. So you can measure some stuff there, but not try to bring it back. I think if you want to try to bring back an ice sample, you're talking about missions that's measured in at least billions of dollars.
You showed tracks that were sort of two characteristic shapes, the carrot and the turnip, I think you called them. Do you understand what's going on in particular the turnip, why it broadens out and then narrows down in that characteristic
Oh, people have
shape?
done some modeling, and maybe in a global way people understand it, but I don't think it's entirely satisfactory yet. I mean, one of the problems is if you ask people to model this whole impact thing, some of them will come back with results where they look you right in the eye and they say every single piece of this particle was heated to at least 3,000 degrees. Okay, well, that isn't the case. So it's got to be that the whole impact process is a highly stochastic one, that parts of the grain give up their life, to protect other parts of the grain. And so I think so far the modeling that's been done doesn't have sufficient fidelity to take that kind of effect into account. And it's a little hard for us to provide them with good information to base their models on, because you can go to the light gas gun here, you can go to the vertical gun here at Ames, and you can shoot mineral grains in. And so we have lots of data on these carrot tracks and so we can take the diameter of a track and the length of the track, and we can use that based on the aerogel we have to predict, what the mass and the velocity of the particle probably were, and so on. But we can't accelerate fragile things. We can't accelerate these aggregates. They come apart. The closest we've ever come is Fred Hertz at Johnson Space Center once managed to accelerate to 6 kilometers a second a sample of Nestle's cocoa powder. Okay, so so there's some fast hot chocolate for you. And the net result was a series of bulbs. They didn't have any of these terminal tracks going at the bottom because there was nothing hard mixed in there. And when we measured that, we found that a lot of chemistry had happened in that stuff. But we also see things that have been in the Stardust samples that have clearly been cooked way less than we saw that cocoa powder. So sometimes the organics can survive because the mineral grains are there to protect them. And so far the predictions made by the models kind of qualitatively explain what we see, but they, quantitatively, I'm not sure, how informative they are yet.
Scott, now that we have, or at least we're beginning to have, this rich set of data about the microstructure of a comet, basically, and we have data on the microstructure of very primitive meteorites, is anybody putting together a self-consistent model of how you make both the most primitive carbonaceous chondrites and how you make a comet like Wild-2 in an early solar system, protoplanetary nebula model?
That's a good question. I mean, clearly, the models of the solar nebula existed already that predicted mixing, but nobody made a big deal out of it, or even the modelers themselves, I don't think, thought about what that meant so much. And when Stardust came back and we got these results, suddenly everyone realized, like, oh, it wasn't just a little mixing. This is, mixing on all size scales. And now that's one of the, the be-all, end-alls of the models, is to ask, once you have a model, well, what does it predict for the mixing? And I think a lot is going to come out of that in the long run, although I don't see a whole lot of clarity yet on precisely how we'll use this effect to discriminate between models. And ultimately, Stardust will only give us some clues in that because we have had this high velocity impact. And so, for example, there may be components we don't even know were there because they utterly didn't survive. One of the things, and then there's also the issue that if we got all the grains from 1 or 2 jets, how do we know that's representative of the whole comet anyways? So like in this mission I'm pitching on Friday, one of the things we would specifically do is dip down in and get samples at different points in the orbit, and also make a point of collecting samples where we can keep them separate. So collect a sample from a jet and then collect a sample from a different jet and so on, and find out, well, is it always the same or does it vary? One of the things I find, I think there's got to be tons of information in this, in part because it doesn't make any sense to me yet, is about the timing of things, okay? That somehow you had to get some of these things really hot and get them back out and get them mixed into these aggregates and then get them in the comet. So that gives you really big constraints on how early that had to happen. And at the same time, you've got to have stuff that comes in from outside and never gets hot, even slightly, and then they got to get together at the right time and place to all end up in the comet. And then just to make it more complicated, this is the one that really puzzles me. How do you have the interstellar isotopic anomalies be reasonably common and have the circumstellar grains be reasonably uncommon? Because naively, you would expect the circumstellar grains to be the cores on which ices are condensed and on which you made the interstellar organics. So why aren't they traveling together? And if they are traveling together and then they get separated at a later date, how come the fragile organics survive, not the robust circumstellar grains? So there has to be some serious clues about the timing of things in that, and I still haven't quite got my head wrapped around that one.
You had mentioned that one particle, osbornite, was you believe was the result of a high temperature event, maybe a star explosion. Would an event like a thermal event like an asteroid impacting a planet or a volcano be sufficient heat to
Well, I'm not a super expert at mineralogy, but I think the answer to that is no. I mean, basically, when you get osbornite, and according to models, is if you take a gas of, so this is not, probably the osbornite does not come from an outflow of a star. It probably is associated with our solar nebula. As far as I know, the isotopes in that grain are completely solar that they've measured, if it's big enough that they've been able to measure many. But if you took a gas of solar composition, in other words, you took the whole solar system, everything in it, sun, planets, asteroids, comets, and you vaporized it, put it in a box, and then you let the temperature in the oven drop. The gas will cool, and at some point something will start to condense. Okay, and the things that will condense are the most refractory minerals, and this osbornite is one of those. And so, in a gas that's roughly solar composition, osbornite would be one of the first things to form. But if the gas doesn't have solar system abundances but has a higher proportion of oxygen or whatever, it may not form. Something else will form first. Okay, and so in an impact, you might get vapor that's at this temperature, but the actual composition of the gas would be very unlikely to give you the osbornite as a condensate. In addition, in something like an explosion like that, things have to condense really fast, whereas we see things that are crystalline, which implies they condense a little more slowly. So I think that I won't say no to that possibility, but I think the main thinking right now is that probably we're looking at grains that must have formed out of the solar nebula way in close to the sun, where things were basically getting completely torched, and then that material somehow had an opportunity to cool by mixing outward or getting screened by something else or whatever. And then that gas, as it started to cool off, first formed osbornite, and later it started to form, a less refractory but still very refractory minerals like some of these other minerals I showed up there. And as it just cooled more and more, you got more and more stuff come out. But that osbornite was one of the very first things. I think that's the general thinking that most people are running with at the moment, anyways.
Great. I guess this will be the last question.
Getting back to the organics, obviously you're saying there is chemistry going on when they're impacting into the aerogel. So how much of the results you're getting from the organics do you believe to be actually indicative of what's actually out there on the comet versus stuff that's gone on? And the second part of the question is, given that you're seeing a lot of pHs, unless you know that they are original, how do you know they're not chemistry and that some of the other lighter elements, oxygen and hydrogen, haven't actually combined with some of your more refractory minerals as well and generated some of those?
Well, I mean, this is an issue, and it's going to be an ongoing one, forever, basically. But and my answer has to be a little complex. I think when you see a material that's present and it's a fairly robust material capable, where it would be capable of surviving a certain amount of heating or whatever, you have to be suspicious that this could have been formed by, let's say, the impact. Okay, but if you see a material which is extremely volatile and would not have survived any kind of heating, then it's unlikely that you made it by heating. So so one of the things we do all the time is we take our organics and we plot them on various plots with different axes where we can compare them to, let's say, terrestrial organics or something. And you'll say, oh, on this particular plot, there's a trend that things that are very amorphous are up here, and then stuff that gets heated goes this way. And then you say, well, where do we fall on this plot? And you find out you have points that go along the whole thing. So there's a couple possibilities there. One is that all of those existed in the comet, or the other is that maybe you had some of this more volatile stuff on the comet, and some of the stuff you see down here at the heated end was all made, by the impact process. So it would be more problematic if everything we saw was always a refractory organic, because then you would say, well, every one of these atoms and molecules could have been, rejumbled during the impact collection. But the fact that you see these isotopic anomalies, and some of these isotopic anomalies are in these very volatile materials, suggests at least some of the stuff is definitely from the comet. And this is also an issue of a matter of degree. Maybe some stuff got changed a little, and then how would you recognize that? This is a problem that we'll just have to struggle with all along, but this is also one of the prime motivations for me going to headquarters and saying we want the next mission, is that if I can get material collected at 1 meter per second and I can get 1,000 times as much stuff, I won't have to worry about these problems anymore, and I'll know for sure. There's no doubt that at least some of the organics we see have to have been processed to some degree. I mean, it's just impossible that it's all pristine. And we also have a strong reason to suspect that at least in some cases, like these really lightweight PAHs we see where there's no other organics around, that those may be completely secondary products and have nothing to do with the comet. But the really volatile stuff and the stuff that's got the nitrogen and deuterium enrichments, I think that's largely unaffected. I mean, even if you heat those modestly, they either would have been altered to be more robust materials, and or they would have isotopically started to equilibrate with everything around them. So at least some of the stuff did a remarkably good job of surviving the whole trip.
Good. Well, let's thank Scott very much for an interesting, entertaining seminar. And Scott, good luck on your pitch on Friday.